Hello and welcome to Train Signal. You are watching a lesson about Linux hardware settings. As we begin the first of our lessons, I think it's important to take a moment to set the stage a bit. If you're like me, you've probably come to Linux following a long, exciting, and maybe just a little bit of a tumultuous history with Windows. If you can believe it, I obtained my MCSE when Windows NT 4.0 was the hottest networking software. We've chosen a career path wrought with change. Over the years, you've probably installed, supported, troubleshooted, and may have even provided training for a variety of systems, software, and operating systems. And whether it's for professional reasons, or like many techies, just out of curiosity, you found your way to Linux. And I'm glad you have. You'll find the Linux community a fiercely loyal, tight-knit group, always willing to extend a welcoming hand to the newly converted. We have a lot of information to cover, and I'll do my best to present it in a format that's easy to digest. When there are relevant or similar concepts in Windows, I'll be sure to note those, as this will help with your transition. And for those pursuing the CompTIA Linux Plus certification, this course maps directly to CompTIA's published objectives, which is why we begin with the first objective, Linux hardware settings. In this lesson, we'll cover IRQs and how they relate to specific hardware, I/O and DMA addresses and how they facilitate communications between hardware and the Linux operating system. We'll review boot disks and the associated geometry, then examine the differences between cold plug and hot plug devices. Next, we'll take a look at expansion cards and how to configure them, Linux drivers, and kernel modules. And this lesson wraps up with USB and hard disk device configuration. Up first, IRQs. Before we get into the inner workings of IRQs, I should probably say that you may not spend a great deal of time tweaking these settings, except in the case of troubleshooting. We cover it in detail here because it is part of the Linux Plus exam objectives, and for those of you pursuing certification, you'll need to know this information inside and out. So without further delay, let's dive in. Just like Windows, Linux systems have a variety of hardware that perform a variety of tasks. Your video card controls the monitor. A sound card does the same for your audio. Theoretically, your system could send a signal to your video card to display something on your screen, and then wait patiently for that task to finish before doing anything else. Such a computer system wouldn't be much fun though. You'd spend half your day waiting for one task to complete before another begins. A more efficient way is for a device to be able to make a request, then let the system go on to another task, and have that first request interrupt when it's finished. So there has to be some hardware support for the devices to interrupt whatever the CPU is currently doing. Imagine sitting at a Linux developers conference. Your instructor just said something you don't understand. So you raise your hand and ask a question. Once she answers, she continues on with her presentation. On your computer, this is where interrupts come in. An interrupt request, or IRQ, is a signal sent to your CPU which essentially says, hey, stop whatever you're doing and take care of something else. Some interrupts control specific hardware, like your keyboard or the system timer, while others have multiple uses, and some are left open for new hardware or devices that you may add to your system. Now you may be wondering exactly which IRQs are in use on your system. To do that, we review the contents of the /proc virtual file system. This directory contains dynamically created virtual files that are like little windows into the current state of the Linux kernel, providing information about hardware, processes, and the like. But this file will only show IRQs for drivers that are already loaded. Let's take a look at how we can identify which interrupts are currently being used. From the Applications menu, if I click on System Tools and click on Terminal, that will launch a terminal window. Now this might be a bit different in your distribution. I'm using again Fedora 13. Now from the command line, we'll type in the command cat, C-A-T, /proc, /interrupts. We'll review the cat command in more depth in a later lesson, but for now you just need to understand that this command will display the contents of a file. And we'll hit enter, and scroll up a bit. The important columns are the first one here and the last. And you can see that IRQ 0 is applied to the system timer, and my sound card here is again applied to IRQ 5. Some of these will be easy to recognize and others not so much, but a quick internet search will often reveal the purpose. Now let's review the default system IRQs. For the purposes of the CompTIA certification, you'll need to memorize these IRQs numbered 0 through 15 and their usage. They are typically assigned as indicated here. First we have IRQ 0, which is assigned to the system timer. That's one that's reserved for internal use and shouldn't be reassigned. Same goes for IRQ 1, which is assigned to the keyboard. IRQ 2 is a special case, and it's called Cascade. In the original x86 architecture, there was only room for 8 IRQs. Using this cascade number, that number can be bumped up to 15. IRQ 3 is assigned to the second RS-232 serial port, but can also be shared by a fourth RS-232 serial port. IRQ 4 is assigned to the first serial port, but can also be shared by a third. And IRQ 5, as we saw in our display just a moment ago, is assigned to a sound card or a second parallel port. The system IRQs continue with number 6, which is assigned to the floppy disk controller, and number 7 to the first parallel port, which is Windows LPT1. Number 8 is assigned to the real-time clock. IRQs 9, 10, and 11 are left open and can be assigned accordingly. And we've got IRQ 12, which is assigned to the PS2 mouse. We continue with IRQ 13, which is assigned to the math coprocessor, and this is another one that's reserved for internal use. Last two we have is IRQ 14, which is assigned to the primary ATA controller, and 15, which is assigned to the secondary ATA controller. And we'll review those names a little bit later, so don't worry about what they mean at this point. Now you may have noticed that some of the IRQs in the table have multiple uses. And you're right, this can cause conflicts. A common one is with IRQ 5, which is assigned to both the sound card and the second parallel port. But with today's newer PCI buses, those conflicts are a lot less common. In addition to interrupts, system devices also need what's called an I/O address or an input-output address. We'll talk about those next. Input-output or I/O addresses, also commonly referred to as I/O ports, are memory locations set aside for communicating with certain hardware. Like IRQs, they shouldn't normally be shared as conflicts can arise, but in truth these are more rare. Think of an I/O port like your home address. For a letter to reach you, the sender has to have this information. Similarly, each device on your system must have an address for other components that need to communicate with it. This chart outlines some Linux devices along with the IRQ and I/O port. As you can see, the address is written in hexadecimal notation. And thankfully, you don't have to worry about memorizing these, but you do need to understand the basic concepts around I/O ports and how to view them. And now, this is a good time to take a look at how to view the ports that are in use on your own system. Similar to IRQs, you can view active I/O ports on your system using the cat command. I'm going to switch over to a terminal window so we can take a look at an active system. From the command line, let's type in cat space /proc/IO ports and hit enter. As you can see, the list is quite long. Let's scroll to the top and you can see the memory address on the left, followed by a space, a colon, followed by another space, and then the device name. If you take a look at the third line, you can see that the system time and its address, followed by the keyboard and tons of other devices. For the Linux Plus exam, you should understand the purpose of this file, how to view the contents, and the basic format. I/O ports require direct CPU intervention, but there is an alternative. Direct memory addresses, that offer the same functionality without the performance hit. So next, we'll review DMA. DMA stands for Direct Memory Addressing, and this is an I/O port communication alternative. As the name suggests, devices can directly transfer data without bothering to involve the CPU. Now, the obvious result of less CPU interaction is performance improvements. Not all devices need DMA, but sound cards and some hard drives are examples of devices that may use them. And how do we tell which DMA channels are being used on your system? You guessed it, the cat command. Let's go back to our terminal window and give it a try. From our command prompt, let's type in cat space /proc/DMA. And on my system, you can see that only one is in use, and that's channel 4. Again, make sure that you're familiar with the contents of this file, how to display it, and the general format. Next, let's move on to boot disks. We'll examine boot disk order and geometry. Math was one of my favorite subjects in school, but out of all those courses, for me, geometry was the most difficult. So you can imagine that as I began my foray into Linux studies and stumbled across the word geometry, I was feeling a little less than confident about plunging headfirst into the material. But I quickly learned that my fears were baseless. So you can keep those geometry textbooks packed neatly away into an unused corner of your attic. To begin to understand the technical details of hard disk operation, let's start with the BIOS. We'll cover the BIOS in more detail in a later lesson, but for now, and for the purposes of our discussion, you only need to know that among its other functions, it allows you to set the order of devices from which you can boot your system. Typically you boot from the hard disk, but there are other options, including the CD-ROM or USB device, which has replaced the less common floppy disk option. The BIOS will attempt to boot from the first device indicated, then if it runs into a problem, it'll try the second and third options. If you need to temporarily select a different boot device, hitting the function key during the boot process, like F12 on my system, will allow you to do so. When your system boots, if you look at the bottom of your screen, you should see a message that tells you which function key will access your BIOS. Now this flashes by pretty quickly, so your eyes and your fingers will need to be pretty nimble to catch it. Using a removable disk to boot your system does leave you open to a few security issues. For instance, someone with physical access could easily use a floppy or external drive to boot the system. For this reason, it's best to boot from the first hard disk. Typically, the BIOS can detect and properly configure devices, but sometimes it may need a little help. To understand why, we need to think about early hard disk layout, where you have read-write heads, like the one you see on the image on the screen, that move across the surface of disks called platters. As the disk spins, the head marks circular tracks that make up a cylinder. And each track is further broken down into sectors. So if we put that all together, sectors can be identified by the cylinder number, the head number, and the sector number. Those three numbers make up the CHS code and was used by older BIOS versions. But thankfully, modern hard disks can relay this information automatically. But for those of you who may have a few older disks still laying around, you can and may need to set the CHS information manually. Modern disks don't use a fixed number of sectors like their predecessors, so CHS codes may be less than accurate. And because of limits in the BIOS and ATA hard disk interfaces, CHS geometry tops out at 504 megabytes. Certainly not the typical size of hard disks today. CHS translation can expand that to about 8 gigabytes, but there is a new option. Logical block addresses, or LBA, use a single unique number assigned to each sector on the disk. With the correct sector number, the disk firmware can read the correct head and cylinder numbers. So given the choice, LBA is the best choice today. Next up, as we continue our look at Linux hardware settings, are cold and hot plug devices. Early on, when USB pen drives first hit the scene, I plugged in my little 256 megabyte drive backed up some important data, and ripped it right out of the port. I know, you can guess what happened. Later on, plugging the device back in, hoping to find my files, I instead found an empty, corrupted drive. It's something that probably happened to everyone at one time or another, or maybe that's just something I tell myself to feel better about the whole thing. But the point is, that was my first hard-earned lesson about the difference between cold and hot plug devices. The Windows equivalent term is hot swappable. So we know system hardware can be broken down into two categories, cold plug and hot plug. Cold plug devices can only be attached or detached when the computer is turned off or is cold. Typical cold plug devices are memory, the CPU, or the hard disk. Conversely, hot plug devices can be attached and detached while the computer is on. USB thumb drives or FireWire cameras are typical hot plug devices. The important thing to note is that you should first unmount these devices before you detach them. Let's move on and review how to manage hot plug devices. In order to manage hot plug devices, Linux uses 4 utilities. Before we talk about them, we first need to understand 2 key terms. A daemon, luckily not the kind that you read about or see in the movies, is a program that runs in the background at all times, waiting for some occurrence to happen. And a user space program is one that no matter if a regular user or root runs it, it is still run as an ordinary program. The first utility is dbus, or the desktop bus. This runs as a daemon and enables communication between processes and gives them the option to be notified of hardware events or even other processes. The next is the HAL daemon, or the Hardware Abstraction Layer daemon, or HAL-D, is a utility that provides user space programs information about available hardware. sysfs is a virtual file system and is mounted at /sys. It exports information about devices. And the last is udev. This is another virtual file system that's mounted at /dev, and it dynamically creates device files as drivers are loaded and unloaded. You configure those through the /etc/udev file. Now let's move on to expansion card configuration. We'll start with PCI cards. PCI stands for Peripheral Components Interconnect and is a type of system bus. A bus simply lets you connect components to the computer's processor. Some typical components include hard disks, memory, or sound or other expansion cards like you see in the image here. Devices that run off your PCI bus are normally automatically configured, but if you're feeling adventurous, there are several options that you can tweak yourself. The Linux kernel's PCI access mode determines how it detects PCI devices. The options are through the BIOS, through mmconfig, Linux Direct, or any. Now any is probably your best option. It'll first try mmconfig, then direct, then the BIOS. setPCI is a utility that allows you to query and modify PCI configurations. The syntax is setPCI space options space devices space operations. Now this isn't a tool that you're going to use very often, but we do need to be aware of it for the exam. You may only use this in cases where you already know the low-level configuration. You might use this command, for example, to change the latency timer or to list all devices in a particular slot. The lspci command can be used to see how PCI devices are currently configured. To help refine your output, this command takes several options, the most common listed in the table over the next 3 slides. The lspci command can be used alone, but again it also has a number of options that you should be familiar with. Each option is lowercase unless otherwise indicated and is preceded by a dash. So the command will read lspci space dash option. As a certification exam tip, you will need to memorize this command and all of its options. First we'll go through each of them, then try out a few in our terminal window. The first option, -V, means to increase the verbosity or depth of the output. If we were to type in LSPCI without any options, we'd receive a single line listing of all the PCI cards in our system. But if we were to try it with the -V option, we could see that the output would be expanded to multiple lines and would include additional information like the kernel, different modules, or regions. The next option, -N, displays the result using number codes instead of the device or manufacturer name. And the "N" option displays manufacturer and device name along with the numeric code. -X is an advanced option that displays information in a hex dump. Continuing with options for the LSPCI command, up next we have -B, which shows IRQs and other data as seen by devices instead of the kernel. -T employs the use of a tree view to show device relationships. -S, you'll notice, has a bit of a different syntax. This will display only devices that match the indicated specifications. -D restricts output to data for the specified device as indicated by the vendor and device name. -I file uses whatever file is specified to map vendor and device IDs to actual names. The default file is /user/share/misc/PCI.IDS. Next, -M will display the data in machine-readable format. This is typically useful if you want to pass this data on to a script for further processing. D displays the PCI domain numbers. M is used by root to perform a scan in bus mapping mode. This can reveal devices hidden behind a misconfigured bridge, for example. And finally, we have the -version option. As you may have guessed, this displays version information. Let's try out the LSPCI command with a few of these options. Let's switch to our terminal window. First, let's type in LSPCI without any options. Again, we have a single line listing with each of the PCI devices that are identified on our system. Now, let's try it with the -V option. And we'll scroll up so you can get a better look. Here we go. Again, you see the output has been increased. We have additional information, again including kernel information, driver information, ports, etc. And that it's extended over several lines. Let's try one more option. First, we'll clear the screen so we'll make it easier to read with the clear command. Then we'll type in LSPCI. Let's try the -N. This, as you can see, displays the numbers and codes instead of the device or manufacturer name. In Linux, hardware is handled by kernel drivers or kernel modules. In Windows, these are called drivers, and in fact, you might hear the same term in Linux circles from time to time as well. These files are usually stored in the /lib/modules directory. Files are loaded and unloaded to provide or remove access to a particular piece of hardware. The lsmod command will tell you which kernel modules are currently loaded on your system. Let's switch back to our terminal window and try this out. From our terminal window, if we type in lsmod and hit enter, scroll up, we'll see that the module name is listed in the first column, followed by the size, and the last column tells you what's using the module. This could be a process or even another module. Normally, Linux will load all the drivers it needs when you boot your system. However, as an administrator, there are times when you may need to load modules, mainly for testing or troubleshooting issues with automatically loaded modules. You can do this with either the insmod or modprobe commands. Ensmod syntax must include the full path and file name with extension of the module and sometimes can take additional options which may be outlined in your module's documentation. You can run into problems using Ensmod if there are unmet dependencies. So if you try to install a module that depends on another one that isn't installed, the command will fail. And this leads us to modprobe, which does not require the file name. And another benefit is that any dependencies are automatically loaded. Modprobe relies on configuration files and can take options to tweak its behavior. The syntax is modprobe space dash option space command name space module name. The first option, dash V, should be fairly familiar by now. It will display additional information as it performs its tasks. Adding dash capital C file name, that is of the module, will allow you to modify the etc modprobe.conf configuration file. Dash N or dash dash dry dash run will perform what's called a dry run, which will perform all the associated actions without actually inserting the modules. Commonly, you'll use this with the dash V option to see what modprobe will do, and this is good for testing purposes. Dash R or dash dash remove will remove the specified module and any dependencies as long as they aren't in use. Dash F or dash dash force, which will load a module even if the kernel versions don't match. Now normally this isn't a good idea, but it may be required with third-party binary-only modules. Dash dash show dash depends, as the name suggests, will show all modules on which the specified module depends. And finally, dash L or dash list shows all available options whose name matches the wildcard. For example, modprobe dash L asterisk F will show all the modules whose name begins with an F. Let's move on to how to remove a module. Now that we've covered how to list and insert modules, it's time to review how to remove them. This probably isn't something that you'll do regularly, but troubleshooting a misbehaving module is one instance where you may need to try it. The command is rmmod, and the syntax is relatively simple. You type in the command rmmod space module name. Like the other kernel module commands, rmmod takes several options. Dash V, as we've discussed before, will increase the verbosity of the output. Dash F or dash dash force will force removal even if the module is in use. Dash W or dash dash wait will remove the module when it becomes unused. Other options are listed on the man page for this command by typing man rmmod. Like ensmod, rmmod will fail if the module indicated is a dependency of another module. If you're wondering what the difference is between this command and modprobe-r, you're not alone. This was something that also confused me initially. The latter command will actually remove the indicated module and all those upon which it depends. This is called the module stack. Now just a second ago I mentioned the man page. I suggest for this as well as other commands that you consult the man page. And this page is basically like an entire Linux manual that you can access from the command line. Let's take a quick look at a sample man page. We'll go over to our terminal window. From our terminal window, let's type in man space rmmod. What you'll see here is the command name, followed by a synopsis and a description, and its options. You can scroll down using your arrow key, and you can type Q to exit and quit the program. Now, let's go back and take a look at configuring USB devices. USB drives splashed onto the scene, and within a few years, thanks to higher data transfer speeds and device portability, have usurped serial and parallel ports as the most common external interface. Two utilities help manage USB or what's known as hot plug devices. USB Manager, and Hot Plug. USB Manager runs in the background, like a daemon, and detects changes to the USB bus, loading or unloading kernel modules for the device. Configuration files are stored in etc USB Manager at /etc/USB-mgr for specific devices and /etc/USB-mgr/USB-mgr.conf for overall configuration. USB Manager's use is declining though, and this is due to the shift from in-kernel drivers to those in the /proc bus USB file system. Again, this is a virtual file system. As of the 2.4x Linux kernel release, most distributions now use the Hot Plug package. With this package, files are stored in the /etc/hotplug. There are two notable files: etc hotplug/usb.usermap, and this contains a database of USB device IDs and pointers to scripts in etc hotplug USB that are run when devices are connected or disconnected. The ls USB command will tell you which USB devices are in use on your system, and like other commands, its output can be tweaked using various options. -V you will recognize as the verbose option. -S with the bus and dev num parameters restricts output to specified bus and device numbers. -V with vendor and product parameters limit output to a vendor and a product. D space file name will display information about the device accessible via indicated file name located in /proc/bus/USB. -T will display the device list as a tree. And finally, V or --version will display version of the ls USB utility. Coming up next, we'll go over how to configure hard disks. The hard disk could be described as the backbone of your computer. Storing your operating system and all your files, I don't think that's much of a stretch. There are three most common types of hard disks that you'll find today. The first is PATA, or Parallel Advanced Technology Attachment. This uses a parallel interface where several bits are transferred over the cable at once. You're more likely to find this drive type in older computers. They typically have 3 connectors, 1 for the motherboard and 2 for the disks. Disks must be configured as masters and slaves, preferably on separate controllers, as each has a limited throughput, easily exceeded by the 2 drives. In Linux, these disks are identified with the /dev/HDA or HDB designation, with the first being the master drive on the first controller and B being the slave on the first controller. Gaps can occur in the numbering. And as for optical media, /dev/CD-ROM or /dev/DVD are common designators. The second type is SATA, or Serial Advanced Technology Attachment. You'll find these on most modern computers. SATA differs in that it connects to the motherboard or controller on a one-to-one basis. You can't connect more than one disk to a single cable though. And this is a serial bus, so only one bit of data can be transferred at a time, but it transfers more bits per unit, so it's faster. Most Linux SATA drivers treat these disks like SCSI disks, which we'll talk about next. SCSI, or Small Computer System Interface, is typically found on higher-end systems, and that's because of cost. And it can come in both parallel and serial versions. These drives support up to 8 or 16 devices per bus, depending on the type. The host adapter is usually built into the motherboard or may come as a plug-in card. Unlike the other 2 hard disk types, these aren't automatically detected by the BIOS, but you can still boot from this disk if it has its own BIOS that supports it. Hard drives follow this naming system: /dev/SDX, with X being a letter starting with A. Tape drives are named /dev/STX and dev/NSTX, and X is a number starting from 0. CD and DVD ROMs are named /dev/SCDX or dev/SRX. Again, X is a number starting at 0. One thing to remember is that some devices like USB drives and SATA disks are mapped to the Linux SCSI subsystem. So the SCSI ID assigned to a device has no real bearing on its actual location. The last thing I'd like to note here is that the issue of how external disks fit into this scheme. External disks can be USB thumb drives, FireWire, or even another SCSI device. And as I stated before, these will be treated like any other internal SCSI device. So if you plug in, you'll see a /dev/SDX device node appear. Certification candidates should thoroughly understand these hard disk types as well as their naming conventions. And with that, our lesson concludes, but first we'll take a moment to review what we covered. We've covered quite a bit of material in this lesson, and nobody expects you to remember everything the first time through. Instead, you'll probably want to review the material again and perhaps again. And you need to also take some time to work through the terminal demonstrations. I found this is the best way to retain the information. To recap though, in this lesson we began with a look at IRQs and how they're used by the system hardware to gain the attention of the CPU. Then we talked about how I/O and DMA addresses are used to handle communications between hardware and the operating system. We reviewed boot disks, the difference between cold plug and hot plug devices, and expansion cards and how they're configured. Next, we covered Linux kernel modules, and this lesson concluded with a look at USB and hard disk device configuration. Thanks for joining me.